Hello and welcome everyone to today's JMP Academic webinar, Tune and Zoom, a method for tuning machine learning models that you and your students can use. I'm Ross Matusalem. I'm an academic ambassador at JMP, and I'm just here to host and manage Zoom and our Q&A because today we have a special guest presenter, Professor Nathan Coates from Villanova University, located in Pennsylvania here in the United States. Professor Coates is an associate professor of practice in the Villanova School of Business, and he's the faculty director of the Master of Science program in Business Analytics and AI. And he's a good friend to JMP as well. He has extensive experience teaching predictive modeling, and today he's going to share with us a method for tuning machine learning models, Tune and Zoom, that he's developed over years of teaching and has successfully taught to many students in his program so that when they graduate, they're really ready to tackle real world predictive analytics problems. So Professor Coates is going to share with us how Tune and Zoom works, how well it performs, and how he teaches it in the broader context of his class. So we're grateful to have Professor Coates with us today to share his knowledge and experience, and I expect that all of us are going to take away something that we can use with our own students.
Thanks,
Before we
Ross.
get started,
Oh, sorry.
oh, that's all right. Just a quick note to everybody. I encourage you to ask questions throughout using Zoom's Q&A. So feel free to use the chat for general comments that you'd like to make to the group, but please do use the Q&A for any questions that you'd like to have answered while we're here today. The Q&A interface just makes it easier on our side to keep track of the questions that you all have asked and to present back to you any written answers. So even if you don't have any questions, open up the Q&A so you can see what others are asking and what our responses are. So I'll be in the Q&A fielding any questions about JMP, the software, as we go along. And then for all other questions, we should have time at the end for Professor Coates to take a few from the audience. So with that, Professor Coates, please go ahead and steal that screen share. The floor is yours.
Okay.
All right, looking good.
Okay, great. Thanks, Ross, and welcome everyone. Glad you could join me. Um, Today I'm going to talk about this method that we call Tune and Zoom. It's a fairly simple method for trying to find good hyperparameters for your machine learning models. And so what I'm going to cover today is I'm going to do a brief overview of what Tune and Zoom is, talk about how we teach hyperparameter optimization in our class. Then I'll go a bit deeper into the details of how you would do Tune and Zoom in a classroom environment. And then I'll wrap up with a comparison with a new tool called Bayesian optimization that's in JMP. So I'll use the same description with you that I use with my students, which is when I think about tuning hyperparameters, I think about, how can we find the best parameters for model performance? And the way I think of that is like there's some surface that I can't see where the interactions of different hyperparameter models determine how well my model performs. So I use this analogy of a lake. I say, imagine you're on a lake and you want to find the deepest spot in the lake, and the deepness of the lake is basically a measure of how well the model performs. And I want to find the spot on the lake, the hyperparameters that will lead to that optimal model performance. And you can't see the bottom. So how do we test it? Well, I say, imagine you drop a rock tied to a string from your boat as you row to different positions on the lake. And that's like building a single model. And you look at the results of that model, of how well it performs. Um, and then maybe you go somewhere else in the lake and you test it there. So that's the basic analogy. And so I say, now imagine the lake like you're looking at it from above. So here's our lake, and maybe just think of two parameters, right? Most of these modeling types have more than two parameters, but they're hard to visualize. So let's just stick with two as an example, maybe iterations in learning rate. How could you figure out what those parameters should be? And so what the tune and zoom method does is it basically says, well, just chop that lake up into like a grid and then take a sample from within each grid square, and that'll tell you approximately the depth of the lake. And so, the number of grids that you make, the number of grid squares that you make will determine like how many tests you have to do versus the fidelity of sort of that map you build at the bottom. So in this case, I just have overlaid a 9 square grid. And so I would take somewhere a sample within each one of these grid squares. Then I would look at which one performed the best. And let's say it's this center one. That one had the deepest reading so far, right? Well, what I would do then is narrow my search to within this grid square. So that's the zoom function. I'm zooming in now. I'm not considering all of the possible parameter space. I'm just looking at a subset of it. So then I would repeat the process here. So that's my second, and I'll get to this in a minute, tuning table is how we actually create these grid squares. Here's my second tuning table that is looking at a subset of the search space. And then I would do that maybe a third time. And in general, that's enough to get good results. So maybe that third one is in this square, and now I'm taking refined samples within this area. And sometimes I don't just, when I'm doing this in practice, and what I tell the students to do is you don't necessarily just want to follow the best grid square. And in reality, we don't have a 9 grid square. It's usually like 100. It's like a 10 by 10 grid. I say you're gonna probably find some suboptimal answers in your exploration. So I recommend in practice probably following 2 or 3 of the best ones, and then some of them will fall away, and you can keep drilling down with sort of like keeping 2 or 3 trails through this map going. It's no guarantee of finding the optimal answer. And it's not what I've done in this study either. So in this study that I did, and I'll share the results when we get towards the end, I only followed a single path for tune and zoom to sort of benchmark its effectiveness. And let's see. So that's at a high level how tune and zoom works. I'll get back to more of the details, how to do it in practice in a minute. But first, I want to put it in the context of the course that we teach. We teach a data mining course, and we use JMP to do that. We use add-ins as well, especially XGBoost, and there's some other great add-ins that we use, but we don't do any scripting. So as we're going along and you think of things like how scripting could make this better, just know that we intentionally avoid scripting because we try to cover a lot of material in this class, including like we teach students how to do data exploration with JMP. We teach them how to clean data with JMP, and then we go through a series of models from sort of the most basic to the most advanced. We talk about regression. We go through a few weeks of tree-based models, and then get to neural networks. So we teach them a bit about how each of these models work. So we do, we open up the hood. We look at what is happening during the model building process. And as part of that, we talk about the hyperparameters. And I'll touch more on those in just a second. So another aspect of this course that we should bring up is that we have a semester-long project that we work on. So it's a business-oriented project. I work at business school, so our topics tend to be business-oriented. And so we change our data set that we're working on every semester. And what we do is we chop up our data into 3 batches. We give the students, when the class starts, the first batch, they use that to start to understand all the techniques. So as we teach them data cleaning, data exploration, we encourage them to not only use whatever example data sets that we're using, but also to take this project data set and apply the same techniques to it as we go. And so what they do with the first data set is they learn to clean it, and they learn to build models with it to make predictions. And then we have a practice round. And that is the second batch of data. We give them a data set of similar data, but it doesn't have the target variable, doesn't have what we're looking for. And their job is to build a model and make predictions for that. And they do that as a practice round so that they can be set up for the final round, the third batch of data, and that's what they're really scored on as a big part of their final project. And the way we keep the students up to date on how they're doing is we use a leaderboard. And so this is an example of a leaderboard from last year. I think we had in this class 13 or 14 teams. You see the team names here on the left. We tell them how they did. So like, here's the decision matrix for that they got based on the results for that third batch of data that they'd never seen before. They gave us, they apply the third batch, their model to that, and then they get these results. We tell them things like their misclassification rate, a bunch of the business stuff tied to the profits that this model has generated. And so you see these teams are sorted by the profit they've earned up here. So in this semester, Team Cork had the highest profit. On the very right, we also show what model was selected so that the students can sort of learn and sort of understand for this particular type of data set, which modeling type performed the best. And just anecdotally, usually it's XGBoost and neural nets that win. And with this type of data, XGBoost probably is the winning model about 2/3 of the time. Okay. So a little bit more about profit, because that is the metric that we use to judge our students. And the reason we do that is because we rely on the profit matrix, and the profit matrix is what drives the profitability of the predictions. There are a ton of other performance metrics in machine learning that you could use, like accuracy, precision, recall, these other methods. But they are often skewed, as you know, by the imbalance in the data. So it is hard to judge a model based on just those metrics alone when you have heavily imbalanced data, like our typical data sets usually do. The profit matrix, if you haven't seen it before, it's one of the attributes that you can set for specific columns. And in this case, right, here's a generalized notion of profit matrix where we have our predictions on the top and the actual values on the left. And then we have our true negatives, false positives, false negatives, and true positives. So what happens with the profit matrix is you have to have some level of business understanding. So that's the first thing we teach the students is, where is this data coming from? What's its context within business? What are we trying to solve with it? So for example, in our class, we use semester long, it's not our final project, but it's another data set we use. It's called the lemon data. It has to do with predicting whether a car is a lemon or not based on a bunch of factors about a car, like how old it is, what the odometer rating is, what the model is, things like that. And we have to understand what the impact to the business is in terms of the profits based on the predictions that we make. And I'll bring up an example in just a minute. But what I want you to know for right now is that you have to assign a dollar amount for each of these four outcomes. And if you can figure out what those are, then you can use profit effectively as a metric for determining model performance. So if you look at the profit matrix for a column, you'll notice that the default values are 1 point every time you're right and -1 point every time you're wrong. So the type 1 and type 2 errors have this -1 here. And if you do the math for this threshold equation, you'll see that comes out at 0.5, right? So the default decision threshold is 0.5 unless you make modifications to this profit matrix. Okay, so here's that example I was talking about. We use a lot of the data sets that come with JMP. One of them is churn. The churn data set, basically, it is a data set you can use to try to predict if someone is going to churn from a subscription business. So think about a cell phone plan or a streaming service plan. So if someone is going to churn, right, that means they're going to leave that service. And so here I have filled in the dollar amounts for the profit matrix for just some assumptions about a generalized churn problem. So let's assume that if someone does not churn, they would have a 0 value. If someone does churn, they would have a value of 1. So if I predict they're not going to churn and they don't churn, they don't leave my service, let's assume our profits from that person for the next year or something is like $1,000. If someone is going to leave, if I predict that they're going to churn, I can intervene. And let's assume I give them a 20% discount. So they only pay me $800 instead of $1,000, right? That's an incentive to keep them to stay. So if someone was actually going to leave me, to churn, they would have a value of 1 under actual here. And if they And if I had correctly predicted they were going to churn, my profit is $800 because I had to give them that 20% discount to stay. Well, let's assume that's 100% effective. Um, Look what happens here, right? If I predict that they are going to stay, to not churn, but they actually were going to churn, my model, my prediction was wrong, then I get $0, right? They've left. Here's the other downside, right? If I have a false positive, if I predict someone is going to churn, but they actually weren't going to churn, I only make $800 on this person instead of the $1,000 I could have if I'd predicted them correctly. So that's sort of the logic behind how these profit matrices work. And if you do the math on this profit matrix, you see I get a value of zero point 0.2 for my decision threshold, which means what? It means, well, if the probability of someone churning, leaving my service is greater than 20%, I should give them the discount, right? That's the most profitable prediction for me to make. If it's less than 20%, then I won't offer them the discount. So that decision threshold is adjusted based on the business conditions. Okay. So let me tell you a little bit about how we specifically teach hyperparameters. So for each model that we use, remember it's like random forest, boosted tree, etc., we define the hyperparameters, and I'll go through an example of that in a minute. And then what we do is we tell the students to basically start with the default parameters. And that's sort of our benchmark. And we calculate what if we just use the defaults that JMP gives us? And we sort of say, okay, our starting point is that much profit, right? I open up JMP. I've got this business problem. I want to build a predictive model. I use the defaults. I hit go, and I have my model with its baseline profit. Now we ask the students, can we do better? Can we get more profit than that? And to do that, we teach two things. One is the tuning table, right? That is a method for more efficiently finding what the hyperparameters should be. And then we also build on that with this method of tune and zoom, using tuning tables to more further refine those models. And then we're very excited about JMP's new Bayesian optimization tool. And so we're going to be integrating that into the curriculum as well, and helping to teach the students when that's the optimal solution versus using something like tune and zoom. Getting back to defining the hyperparameters, I'll just show you guys some slides that I share with my students. So really quickly, like here's the list of 8 of the XGBoost parameters, and we don't go into the more advanced options. We don't do that in this class. We don't have time. But we do go through and we basically will show them like a 2 or 3 sentence description of what's happening within each of these 8 hyperparameters and what they mean. The goal is to have the students be able to understand, well, if I increase this or decrease this parameter, what's the effect going to be on my model? And how can I solve various issues with the model by making these adjustments? So we don't go much deeper than this, just these high-level descriptions of what they are. And there are some interactions between these hyperparameters. So we do talk a little bit about that. And that's part of the reason that adjusting a hyperparameter one at a time doesn't always work, right? Because it depends what the other settings are. We do encourage them to explore, but we also explain that that search space, that hyperparameter search space of where you're looking is actually really big. It doesn't look big when you're looking at 8 numbers you fill in. But if you think about what that really is, it can get very, very big. So imagine I've got these 8 knobs and each one of them has only 10 settings. And we know many of these parameters have many more than 10 settings, but let's just assume for simplicity of 10 settings. What is the size of that search space? Well, it's 10 to the 8, right? Or 100 million different combinations of parameters with just those 8 knobs. So the default parameters probably aren't the best parameters, right? That's why we teach the tuning table, because the tuning table in JMP allows you to run multiple models at the click of a button. And so now you could run 10, 100, theoretically 1,000. I don't ever go that high. I generally run 100 models at a time. Uh, but the reason we do that is it's a lot less work on the human being. The computer has to churn and burn for a while to run through all those models, but that's okay, right? That it's more efficient for the person who's looking for better parameters. So the first pass, just trying a shotgun effect of just take a hundred different random settings on these knobs, you might find something better than the defaults. And so, as my colleague, Dr. Neidig says, tuning tables are a way to work smarter, not harder. And tuning tables are how we create this grid that we search on this lake that I had mentioned before, right? And so we don't actually create these lines. We don't actually set these up. What we really do is use a tuning table. And a tuning table basically creates a sampling space where it takes samples that is similar to a grid. And the reason it does that is there's an option to set up your tuning tables using something called a Latin hypercube. And basically what a Latin hypercube does is it sort of pseudo-randomly disperses these random samples so that they are sort of spread out along all of the dimensions of the hyperparameter space. So for example, I put iterations and the learning rate here. And if you look at this, at first it looks sort of random. But I think you guys can see that if it were truly random, we'd probably end up with a couple of these dots like really, really close to each other. And maybe we'd end up with bigger chunks of white space, right? So this one it's kind of random, but it's also sort of evenly dispersed along this search space. Okay, that's the key. So that's how we create that grid on the lake. And of course, this is not what a tuning table looks like. A real tuning table looks like this, where we have our 8 parameters, and then we have the address in that 8-dimensional space of the parameter set. So these are generated using that Latin hypercube. And it's hard to see from this, but I want you guys to imagine that 8-dimensional space, and I have this tuning table has 100 rows in it. Imagine those 100 points sort of like evenly dispersed in that 8-dimensional space. The tuning tables are foundational to both tune and zoom and Bayesian optimization. So it's an important thing to understand going in if you want to use either of those techniques. So let's go back and talk about how tune and zoom works in a little bit more detail. So in that tune and zoom process, it starts by building a tuning table. And so here, and for all of this study, I used XGBoost. If any of you have used the XGBoost add-in, unlike some of the other processes within JMP, that the tuning table is a separate file that you build yourself, and then you can apply, and you can go customize it and then apply it to the model. The XGBoost add-in has an auto-tune function built right in, where it builds this tuning table sort of behind the scenes for you. And all you have to do is specify the min and max for each of the parameters, and then it sort of builds it for you. My advice in this tune and zoom process is to cast a wide net. Remember, we're searching the parameter space, and JMP has some default min and max values that it recommends. So it has sort of this area that it's going to search. I like to open it up a little bit wider than that at the start. So these 4 parameters I make a little bit wider. And remember, our process will narrow it down to where it should be eventually. So that's not really a problem. I think the number of design points, this is a number of models that are tested within this is like how big the tuning table is by default at 10. For this study, generally I set this to 100. Okay. After we have run all of those, and that does take a while. So if I run 100 models on my computer, which is a pretty standard computer, it takes about an hour to run 100 XGBoost models on my computer. So I go away, I do something else. When it's done, I come back and I look at it. And if I look at the results, it has gone through and used each one of these 100 combinations of hyperparameters, and then it's given me a bunch of performance metrics. And if I have applied a profit matrix to my data table, then I get not only the usual metrics like accuracy and R squared, but I also get my validation profit. So my profit per row is shown to me here, and I can sort my table based on my validation profit. So because profit is what I'm after, that's my metric, and you could easily do this with any other metric, R squared. And if you don't have, if you're looking for something that handles imbalanced data well, and you don't have any profit in your problems, you can use something like F1. That would be another good, a good metric to use. That's sort of immune to the imbalance within the data. Uh, so I have sorted this based on the metric I care about. So my highest validation profit is on top. And so I can sort of see, okay, what parameter settings came out had the best. Now, I remember this is my first pass. Those grid squares are pretty large, so I don't assume I've got the right answer. So what I do is I know this is going to be an iterative process. So what I do is that I then convert this first round results on the left to building my second uh, table, my second tuning table. This is the zooming in part. This is where I've done the tune the first time. Now I'm going to zoom in on a specific area in that lake and explore it in more detail. And the way I do that is I look and I know my best models are here at the top. And I generally look at the top 5 or 10 models to get some guidance and look for patterns within each sort of like the range for each parameter. So, and I sort of give the highest weights to the one that are higher up, but I think you guys can see. I mean, I originally, with the max depth, this first one, I originally was looking at any values between 1 and 12. And you can sort of see, I think you guys can see this. It looks like 3 is probably the right number, but somewhere between 2 and 5, certainly nothing approaching 12. And I don't see any ones in here, right? So then over here, the way I would do this is I would convert my next parameter range to a value of 3 to 5. I'm narrowing that range down. So the value of 7 is not going to come up in the next time I do this wrong. I've narrowed this down. Oftentimes, though, you can't narrow very much based on what you see here. So if you look at another parameter like the min child weight, and you look at the range here, originally the window that we were looking at there was a value of between 1 and 3. And it doesn't look like it's narrowed down very much from that, right? So I said, well, I'm going to narrow this down a little bit, somewhere between the min child weight, somewhere between 1.1 and 2.8, which is percentage-wise in terms of the range. I haven't shrunk it very much. And so that can be a little unnerving as we do this process. And so some parameters are going to shrink a lot, some aren't going to really shrink at all at first. But I don't want you to be concerned about that. And here's why. Remember, what the process of tuning and zooming is doing is it's excluding part of that search area to get around the areas that we think are the most important. And so here, what I've done is I've graphed the reduction on each dimension on the x-axis. So this is how much the dimension has been reduced. And I think maybe I had reduced that min child weight by 10%, let's say, going from 1 to 3 to 1.1 to 2.8 is about a reduction of, I think, yeah, about 10%. There, maybe it's a little more. If I had only reduced each of my dimensions by 10% across all 8 dimensions, like hardly shrunk them at all, that still has the effect, if I look at this curve over here, of reducing the search space by 57%. So I've excluded 57%, right? So, or if I had reduced each of my dimensions by 25%, that would reduce my search space by 90%, right? So there's a nonlinear relationship between what's happening on each dimension, what's happening to that whole search space. So the reason I'm telling you that is don't be concerned if some of the parameters don't shrink very quickly. Okay. So just to review the tune and zoom process, it starts with a tuning table. I recommend something like 100 models. Then you sort the resulting table based on whatever metric you want. For me, that's validation profit. You find the best range of parameters, and then you zoom in on that range. It's a pretty simple idea. You might be underwhelmed at this point, but it's okay because this is a technique that we're trying to get the students to understand, to wrap their heads around. How would you even begin to search this enormous space? The third step in the process is zooming in, and then you do this whole process. And I recommend doing this process 3 times. Uh, you could do it more times than that, but we do want to avoid like hacking validation parameters and sort of intentionally overfitting our model. So I think 3 times generally gets you within the right range. And so if I do this 3 times, I have my last table that comes up. I'm not going to zoom in anymore. I have to actually make a bet on some parameters. So I'm just going to again, I'm going to sort this based on validation profit, and I'm just going to grab the best parameters here. And those are the ones I'm going to go with. So after I've done this 3 times, I grab my top parameter set, I plug those in, and I create a new model with just those parameters. Forget the tuning table now. It's just those parameters. And I build a model. And what I've done here is, I think in general, validation metrics are fine to use, especially with something that uses like a k-fold. I think those are going to be pretty accurate. But just to be sure, and for this study, I did this too, we have a holdout data set. So we have a third partition of our data, a test set. We bring out of the vault when the model is done, and we basically say, now show me how well you conform on data you've never seen before. And that is, when I show you the results in a minute, that is the measuring stick that we use. Okay. Let's talk a little bit about a Bayesian optimization. So this is new with JMP 19, so it's pretty new to me. I've just been playing with it for a couple of months. And you can see it's under this analyze menu item. It's under specialized modeling, and there it is in Bayesian optimization. And what this is basically does is it creates a model where whatever metric you care about, remember validation profit is what's driving my model selection. I cast that as Y. That's the target variable. And then I put in all the hyperparameters as my X variables and basically build a model that tries to predict which hyperparameters are going to lead to the best validation profit. And so this is how Bayesian optimization works. It basically tries to take a set of data points that you give it, and the data points we give it are a tuning table. So the same artifact that you use to start tune and zoom, you also could use to start Bayesian optimization, right? Because it has all those hyperparameters in it in the tuning table plus the metric that you care about. And so imagine that metric I care about, validation, is like this y-axis here, this fx1. And then these x1 and x2 just represent some arbitrary hyperparameters. This curve is drawn using this Gaussian process to basically try to figure out where the peaks of this are. But remember, this isn't a true mapping of the performance of this model. This is an extrapolation of the data points you've already given it. So one of the great things about Bayesian optimization, though, is unlike tune and zoom, which would tend to favor this area probably, the Bayesian optimization also spreads around its investigation and will do more testing in maybe some of these secondary or tertiary regions that look good. So that's exciting. So you could think of this surface here as either a map of profit, or it's the same thing as the bottom of the lake in a way. Okay. So Bayesian optimization, let's go through the process of how that works. And it starts, like I said, with a tuning table with the results already done. And you also have to set the response limits to that. You don't have to set them to any values, but this is just part of a checklist. You have to set a response limit or set them to nothing. Once you do that, though, you can analyze this using the Bayesian optimization model and get the output of that process. And that output looks like this. I have this Bayesian optimization output that will pop up, and there's 3 tabs on it. I haven't found anything that I look at too much in the model summary. Mostly what I do is go right to the batch selection tab because what's in there is a listing of the best parameters that the optimization technique has come up with. So it thinks based on what I've given it so far, it creates that surface. It says, this is the peak of that surface right here, these parameters. And it says the reason added is this max expected improvement. It thinks these are the uh, the parameters that are going to work well. This reason added is also, let me just do a little sidebar on that one. This is where you tell what state you are in the Bayesian optimization process. So as long as you see the max expected improvement, that's basically a signal that you should continue to do this another round. So just like with tune and zoom, Bayesian optimization, to do it well, you're going to go in rounds. This is the first guess that the Bayes op model thinks is right. But if it says max expected improvement, that's a clue that you should probably move forward and do a second round. And you do that by clicking this Make Table button. When you click the Make Table button, something interesting happens. It will add the 101st row to your data table, so your tuning table. So here's my tuning table. I've got the recommended parameters written there already. So you can see it said, we think the max depth should be 4.8 and the subsample rate should be 0.998, etc. But it does not contain the validation profit because it hasn't actually run the model on the real data. The only data used in Bayesian optimization are the hyperparameters and the validation profit. And for this 101st row, it can't figure out what that profit should be without running a model. And so what you have to do is then sort of go back to your original data table, build a single model using the parameters that are recommended by Bayes opt. And once you have those, then you can fill them in right here. Okay. Once that is in there, you now have a table with 101 rows in it that have both parameters and validation profit. So the next thing to do is to click this script that has been automatically created by JMP. And so if you do this Bayes op startup for batch one and you click this button, it will rerun Bayesian optimization for you, but now include all 101 rows. Starting the process over again. So here's the process map for Bayesian optimization, right? You start with the tuning table, like I just said. You run that script, which gives you the Bayesian optimization model output. If you click the Make a Table there, it will write that new row over to your tuning table, but you have to step out of the optimization model and go back to your original data table, build a new model with the best parameters recommended by Bayes opt, get the resulting validation profit, and then that will add to your tuning table. Then you run the process again. This has ended for me in as few as 2 cycles, but that's not common. Usually it's 3 or 4, but a fair amount of the time you have to cycle through this process many times. So I, by default, generally start with a tuning table that has 100 records in it. And so it's got a pretty good map of that space that it's looking for, that curve, built by the Gaussian process. But sometimes I would get to like 15 iterations of this process and I'm still not at the end. And so for my own sanity, I created a 15 run limit for myself. And if I got to 15 runs, I'd just take the best one I had so far because I have no idea how many times I'd have to go through this. And I will warn you that if you start with a very small tuning table, like only, let's say, a tuning table with 10 models in it, in general, you're going to end up having to do more iterations through this process because it's got less fidelity in the shape of that curve, that underlying curve. So if you want to keep sane, I recommend using a larger tuning table to get started with the Bayesian optimization process. But even if you start with 100 models, you still might have to, in some cases, iterate through this Bayesian optimization process before it finds what it feels is it's comfortably secure with, okay, I found an answer that's good enough. I think you can also set the tolerance limits for that. I was pushing the limits of how far I could go to find the best model. Okay, here's the results. So what I've done here is I've created a chart that show the improved profits that I have seen based on the data sets that I analyzed using these procedures. And I start over here with my default parameter settings. That's my baseline. So I figured that's the baseline model. That represents some level of profits. And then the rest of these bars show how much I've improved from using the default parameters. So for example, if I use a tuning table, uh, that has 100 records in it, let's say, then I get something like on average a 1% improvement in profits, which usually causes the students to revolt. And so this is something you have to be very careful with, right? Remember that the students thinking about effort and they think about it in terms of grades, like how much effort do I want to go from a 99% on a test to 100%? That's their thinking. Right. And so they're thinking about, wait, I can run the default parameters in 5 minutes and get a model that works. And then if I spend an hour and a half using developing a tuning table, applying that, then I'm going to improve that by 1%. 5 minutes versus an hour and a half, not worth it, right? Well, we like to explain that, these are profits for a firm. And so spending an hour and a half or even an afternoon on making sure that the machine learning model that you're going to deploy has optimal performance. If you can spend an afternoon getting a 1% increase in profits, you are going to be lauded at that firm, right? That is a good investment of time. So we have to like frame it in those ways. So you can also see that, so for Tune and Zoom, it's something getting close to a 3% gain, and for Bayes Opt, it's about a 2% gain. But I am not saying you should use Tune and Zoom over Bayes Opt. That's not what I'm saying. These results are not statistically significant yet. This is a time-consuming process. Each of these bars has only 8 data points behind it so far. I have been analyzing some different data sets and running them multiple times. So just keep that as you guys are getting an early look at this research that I'm doing. So once I get this to statistical significance, I'll add some error bars to this, and then I'll be able to be much more definitive about it. Uh, but anecdotally, from watching students do this for a few years, I think these are about right. So I would guess that I would state anecdotally that I've seen that the tune and zoom method produces better results than just doing a bunch of tuning tables. Which even if this is a bar for doing one tuning table. If you do more than one, this will increment slowly, but nothing like 2 or 3% gain. Okay, unless you get lucky, which is always possible. Okay, so those are the initial results that I have. And let's just compare tune and zoom to Bayesian optimization. So tune and zoom, and part of the reason this is slow is because I've been timing myself in the process of doing this and watching how long it takes my computer to do this, because I think this is sort of helpful in understanding the features and benefits of both of these techniques. Tune and zoom takes about 15 minutes of human labor total. So it's about 5 minutes for each level or layer in that tune and zoom process if I go through it 3 times. And then it takes about something just under an hour to run each of those tables on my machine. So depending on your machine, these times will vary. So this whole process is something like 3 hours, but only 15 minutes of it is my time. Whereas Bayesian optimization, the human labor is more intensive and really depends on how many times you have to cycle through the Bayesian optimization process. And I'm sure that I don't know Bayesian optimization that well. I'm sure there's ways to automate that. And I'm sure with some scripting, it could be done much more efficiently, no doubt, from a human perspective. The total compute time for Bayesian optimization is a lot less. And one set of bullets I had on here that I took off because I don't have good enough data to even mention it, but I'll just mention it in passing to you guys, is that I seem to have noticed that the tune and zoom seems to perform better on larger data sets. So imagine you have like 10,000 rows or more. It seems to outperform the Bayesian optimization. And then anecdotally, the Bayesian optimization seems to do better when you have less than 10,000 records. I can't prove that yet, and I can't explain why that would be true. It's sort of confusing to me, but I can share out more when I get further in my process. on that. Okay. Thank you guys very much. That's my talk. Ross, do we have any questions that we should talk about?
We do, but first, thank you, Professor Coates. I see some hand clapping and thumbs up emojis coming in. We've had some activity in the chat and the Q&A, so I think folks are really enjoying this and got a lot out of it. And that said, we do have a couple questions yet to be addressed. Um, so let's start with the first one. At one point, you said, starting out with about 100 models or 100 runs in a tuning design is a good starting point. Somebody just looking for any more guidance on, let's say sample size, the number of runs, does that 100 depend on which modeling approach you're using or anything else like that?
So the reason that I go with 100 is it's a nice balance for these types of student projects between sort of computational time and the quality of results. So I find the default value of sort of ten models to be too few to really take advantage of the fact that you're automating the process of model running. If you can do, I've done before like 400, a table with like 400 models in it. It just takes a long time. And I don't know about you guys, but oftentimes things like my screensaver timer or something will go off after 2 hours, and then I'll come back and my process isn't even finished because I had to walk away from my computer because it was running for so long. So there's, in general, more models is better, but there's just some like realities and facts of life that sort of limit how far you would want to go in that. So I find around 100 is works pretty well in this kind of case.
Great, thank you. Next question that we have was with reference to assessing performance after that first stage, so the tune stage when you're deciding where to zoom in. And somebody just asked, about the possibility maybe of using some kind of distributional analysis or some other kind of approach to choosing that zoom area. Or they also mentioned maybe some kind of Pareto analysis. Have you explored other options or approaches?
I love those ideas. I haven't just because, I feel like what I do when I look at those is I sort of like give a little bit more weight to the ones at the top, and a little less weight as I go down. And I don't have a hard rule. It's like, I never look below the fifth model, right? If something is, the seventh model and it's got some parameter that's outside the range, maybe I'll keep my parameter window open a little bit to try to capture whatever is happening there. And I don't want to tighten down that search space too quickly. So that's why I don't have any hard and fast rules like that. Also, there's no specific analysis that sort of does what I'm trying to do, sort of intuitively, just getting a sense and a feel of where that window should be. I love the idea of using the distribution, though. You could very easily like look at a distribution. That probably a super helpful way of seeing where you think it should be. I like that idea.
Yeah. And I think you're making, a broader point that I feel like can't be made enough, which is in a lot of these situations, there's always a desire to automate or offload decision making. But in many contexts, it's great to still have a human in the loop making intelligent choices.
Especially in an educational setting. So, we wrestle with this all the time now, especially with the advent of AI. Like, how much should we just let the things be automated, versus what do we want these students to be aware of? What do we want their minds to be wrestling with? And so that's always a challenge, is trying to draw that line. That I kind of like. Even if Bayesian optimization turns out in the long run to be a superior technique, I don't know. I might still encourage the students to try the tune and zoom method just to wrestle with and understand the idea of the search space and what, in some ways, Bayesian optimization is doing under the hood, because I think that's good for their all-around knowledge.
Definitely. We have another couple questions that have come in while we've been chatting. They both touch on similar things, so let me try to synthesize them. Generally asking about applying tune and zoom to methods other than XGBoost, which was the primary example here. So, including methods that might involve fewer hyperparameters.
Yeah. So so actually Boost has 8 hyperparameters. Tuning, so boosted trees and random forest both have 6 basic hyperparameters. And those, the process is different. Those you have to create a tuning table as a separate step in the process, which slows things down a little bit. But this same process can be used there. There in Jump, we have been hoping for a tuning table feature within neural networks, but that's not there, right? There's some sort of random start process in neural networks that basically allows it to start with different random weights that it starts with, and then it selects the best one, but we have no way of peeling back and looking at how it's doing that or have any control over that. And with the weights, it wouldn't matter, but we would like a tuning table for neural networks for the other things like, how many nodes we should have at each layer and things like that. That would be really great, but we don't have that. So uh, definitely useful for the tree-based methods. Can't really apply it to neural networks yet.
Sure. I will mention I dropped a link into the chat because this feedback that you've just delivered is something that we've heard for a bit. And so a colleague of mine very recently using JSL wrote an add-in to try to address that need for the neural network platform to be able to do some tuning. So if you haven't looked already in the chat, go ahead and look. I've dropped a link to the Jump Marketplace, which is just a place where you can download add-ins. So you can try that neural net tuning add-in out. And again, that's a very recent development here.
That's great.
Let's see. Okay, another one. So going back early to the example you used for the profit matrix, can you comment on whether you assume that discounts are 100% effective, and whether, this kind of assumption is something that you discuss with students, and if so, how do you do it?
Yeah, for this example, I simplified things. So there, we assumed that uh, the with the discount that you would apply to someone who's going to turn it is 100% effective. We do more sophisticated analysis in some of our problems where we assume like, okay, assume it's 50% effective. Assume it's 25% effective. And then we ask the students to then figure out what the profit value should be if that's the case. And so then that changes the numbers that go into the profit matrix for true positives because not everyone is going to stay, even if you offer them an incentive. So it can get pretty interesting in the business problems that we give them. But yeah, I like that. Yeah, that's exactly what we do.
Sure. All right, and then we have one more, and this person said, "Sorry, I might have missed it, but at the start, how do you determine the min and max values for the hyperparameters that you want to try, right off the bat?"
So in general, some of the hyperparameters are bound, like the subsample rate or the column sampling rate. Those can only be between 0 and 1, and jump starts with, I think, a default value of zero point 0.5 to 1. And you could make that go from 0 to 1 if you wanted. Um, but there are other parameters like the depth parameter, and that's set by default by 1 to 8. And so one of my first slides, I said, well, I like to open those up a bit. So I try values like 1 to 12, but you could easily set them as like 1 to 20. Um, and so some of the parameters are sort of bound by the definitions of what they can be, but other ones you can open up really wide. So I would say if you don't know about where you should start, just open them up 50% wider or 100% wider than the jump defaults, just as a starting point. And I think the jump folks have done a great job at setting those default parameters. They, in general, work pretty well. And so those default ranges are also thought through, and they're probably going to work great most of the time. I just want to widen that first net that I throw out there just to make sure I'm sort of not missing anything.
Great. Yeah, I couldn't agree more with that advice. Looks like we have made it through all of the remaining questions in the Q&A. So let's just wrap up by again thanking Professor Coates for being here, for sharing Tune and Zoom. It looks like a really great technique, both in terms of, I mean, its performance, but also, and something that students can actually wrap their heads around, get experience with, and master. And so it's kind of the best of both worlds, right? It's an effective technique that students can actually learn to use. So hopefully you all have taken away some things that you can implement in your own class, as is always, the goal with these academic webinars. So I'll just finish one more time. Professor Coates, thank you so much for joining us. Everybody else, thank you as well. And we hope to see you at a future Jump academic webinar.
Thanks, everyone.